So, moving on to our third speaker before the break, Britney Schmidt. And Britney is another one of our great upcoming new astrobiologists. She's a card-carrying astrobiologist, even though her training started out in physics and geophysics, or maybe we should call it planetophysics. But the habitability of worlds and what goes into making that habitable is one of her great passions, and she's spending a lot of time working on that. She is, we're happy to say, a young assistant professor at the Georgia Institute of Technology. And Georgia Tech is now becoming really a major center for astrobiology. One of our NASA Astrobiology Institute teams is there. There are a number of other folks in different departments of that institution. So it's really a mecca for astrobiology. And Britney is going to talk to us about the robots under the ice and how maybe we can translate that to icy worlds. She's going to focus on Europa. And if you haven't seen the program, I direct you to the picture by her bio, where she's a snow queen. And I know that a lot of supermodels would kill for this look. So welcome, Britney.
Thanks, Benny. Thanks very much. I'm also really excited to be here, so thank you so much for the invitation. I'm going to talk to you about Europa and robots and what we'd love to do with them one day. I also wanted to say, since everyone's been sharing their career history, that I met David Smith in 2008 at a meeting in Spain, actually, and it's amazing where you find your friends from graduate school. So this is also work done by my team, which is about 12 people at this point, who helped get this robot under this particular ice. And it will take significantly more people to put something like this under a lot more ice when we get to Europa one day. So I wanted to pose this question, and you're going to see some examples of life here in this video. And I want you to ask yourself, why do you know this is alive? Because really, we're very visual animals, right? We're really try to experience the world through what we see. And I'm going to show you how we experience Europa through what we see, but what is untold about the context that we're missing just with pictures and just with that. And so when we ask ourselves what's really alive, we need to understand a lot more than just, is it moving or does it look like something that's alive? So in terms of context we don't see in this image, there's a few things that are really, really important here. So this is Europa. If you're unfamiliar with it, Europa is kind of the jewel, if you want to call it, of the Jovian system. It's the innermost of Jupiter's 3 large icy moons. And this ice shell that's here on the surface is covered with fractures. That reddish material turns out to probably be part of the signal that needs context. We know it's not pure ice, but we know very little else about it. It's probably salt-rich. The exact salts we don't really know. We know that there's an ocean underneath it, and we don't know that based on images. We know that based on Europa's magnetic field and its interactions with Jupiter. So we know what's underneath it by looking at the fields around it that we can't see with our eyes. There's also something else that's missing in this picture that turns out to be incredibly important. Can anyone venture a guess? There's 2 things I want to highlight. Turns out where the reddish color is really matters. So we talked a little bit about the radiation environment of Europa, and that is an important part of the story. It's incredibly irradiative on the surface. We don't want to live there for an organism. However, what it does is it turns Europa's ice shell into Europa's atmosphere at the same time. It actually turns the surface ice into things like peroxides, which are bad for life unless you cycle them into a reducing environment, the ocean below, allowing you to have kind of a chemical battery that supports organisms, potentially. That's something that's missing on other planets, for instance. So maybe you don't want to live on the surface of Europa because of the radiation, but that radiation that you can't really see in this picture is actually telling you that perhaps this is an important component, providing the oxygen, so the analog for our atmosphere that provides us with lots of energy that goes down into the subsurface ocean. But the other thing that's really, really easy to see is if you thought about the moon, Europa is about the size of Earth's moon, by the way, right? Mostly geologically dead. What is different about this picture? There are no craters, nowhere, right? There's about 2, actually. Everyone knows the names of Pwyll, right? So they know the names of the craters on Europa because there's not very many of them, and that is really the important story here. So we're going to talk about Europa as a dynamic world. So this is taking that image, so that's Europa rise. Let's take the whole surface of Europa, the way that we know it, and spread it out across this image. And what we can see are those fractures that we talked about. There's our famous one crater. There's a couple others in there. But what you're missing there is because the European surface is constantly being reprocessed. There is an internal energy. There's an internal battery. It turns out it doesn't come from Europa itself. It comes from its orbital energy. But that internal battery is allowing the surface to be resurfaced at a very similar rate to that which the Earth resurfaces itself. In about 40 million years, in fact, we can't even age date it because there are so few features that we really understand. One of the other challenges about Europa is that when we got there with Galileo in the late 90s, the main antenna didn't unfurl, so we have only about 10% of the surface covered in what we would call high resolution. On Mars, high resolution, you would see me, you would see this timer that's reminding me not to talk too long, you'd see yourselves. And on Europa, high resolution is anything better than 300 meters per pixel. So we'd miss this room. We'd miss everything about the Stanford campus and most of the images that we have of Europa. And yet we can learn a lot about that by rethinking these images and what it really says. So this reprocessing is telling us that we have a new surface. When we look at it on a number of different scales, we can see these kind of famous fractures. It turns out there's different types of fractures, all of which are important and all of which tell us about the geodynamics of Europa. From these cycloids that we think reflect the tidal history directly, perhaps, these disruptions in the background. But when we zoom in, Europa is a yarn ball on absolutely every scale that we've observed it. There are fractures and tectonic history all across the surface at every scale of resolution. And so this is a challenge for future exploration, but it's exciting because it tells us that this surface has been active for millions and millions and billions of years. Something else that's kind of a fun way to look at Europa's surface, this is what we call a banded terrain. So this is what the image looks like right now, and if you cut out the middle part, you can reconstruct the surface on either side. Anyone know where this might remind us of on the Earth? Seafloor spreading, perhaps, right? So places of activity, places of new crust being formed on the Earth. But this is an ice shell that's actually doing that. So we can actually see, using the static geology, the context of the last several million years of Europa's history. And that's important. We can also see places where Europa is literally turning itself out, right? It's turning its insides out. And so these are called chaos terrains, or these are the small ones called lenticulae. And they're places where Europa's internal activity is disrupting the surface from inside. And they come across many scales. These are about 5 kilometers. And then things that are more on the scale of the entire south pole of Enceladus would actually fit inside this particular feature on Europa. So these are large disruptions of the surface generated by internal activity that we have yet to really understand. So here's some work that we did in 2011 to try to understand these features. And so, oops, I guess that one's not going to play. But essentially what we think is happening is that heating maybe in the ocean or inside the ice shell is causing the ability to melt the ice shell inside it. So we have perched lenses, perhaps, of water, various scales. This is one hypothesis for large chaos terrains, but there's many little disruptions on the surface that we think are linked to subsurface water. That water isn't necessarily coming directly from the ocean, but it doesn't mean it's not liquid water, and in these cases, perhaps as shallow as 3 kilometers from the surface. On Earth, we routinely can drill through 3 to 5 kilometers of ice, so 3 to 5 kilometers on Earth, or on Europa might actually be possible. Some of the really exciting stuff that's happened in the last few years, this is actually from Simon Kattenhorn and Louise Proctor's recent paper in 2014, that detected what we'd all been looking for, but when you only have 10% of the surface, imagine trying to figure out plate tectonics. And so what they found was that there was actually an area of Europa's surface where if you did a reconstruction of the whole geologic history, what you got was about 100 kilometers worth of just missing ice. The geology doesn't replace itself on one side of this fracture versus the other. And so what that told us is that we're actually also losing material. So we're producing new material at spreading centers, much like we see on the Earth. But we're also getting rid of material in a process that right now we call subsumption, mostly because we don't understand how you'd subsume or subduct an ice plate underneath another ice plate. But this is the only other place that we really have confirmed plate tectonic style activity, and it may well be global, explaining a lot of those features that we've seen. So in that one static image of Europa's surface, there's all this dynamics, all this history that's pointing towards an active world with this interesting geochemistry. And so that's really the story, is why Europa? Well, it's because it's so weirdly Earth-like if you can take the Earth apart and put it back together in a slightly different way. In a more traditional way of thinking about it, what really makes Europa special is that its ocean is actually in contact with the silicate rocks. So Europa is incredibly dense, actually 3,000 kilograms per meter cubed. Something like Ganymede is a little bit less. So what's important about Europa is that it actually has so much silicate. So it actually has about 4 times as much water, perhaps, as the Earth does. But what's important is that it has more silicate than other icy satellites. And that ocean is an area that we can actually see is in contact with the silicates. So if the interior is being heated, then we might have Earth-like processes. So this is kind of a simple way of trying to understand Europa's energy budget, but essentially as it's moving around Jupiter in its orbit, it's extremely eccentric compared to a circular orbit. And so there's a huge amount of heat that's being deposited in the ice shell and in the silicate interior. We're interested in that because it's what causes that surface to be dynamic in the first place, but it might be something that's able to, over 4.5 billion years, power the types of geothermal activity that we see associated with life here on this planet. So this is just a picture of a seafloor vent with tons of life teeming from it. And this has been like this on Europa for 4.5 billion years, right? Constant activity for that time. So it's a really compelling place to think about. So that's why we're sending Europa Clipper. Bob Papalardo is the project scientist for that mission. Amongst the things that we'll be able to do is we'll use the 11 instruments on board the spacecraft to sample material that's being flung out. So we'll be able to sample any plume material that's coming by to tell its chemistry. We'll be able to look at the magnetospheric environment. We'll actually get global coverage of Europa, so we can do this kind of science everywhere. But what's really exciting to me is this radar instrument that will actually take kind of an X-ray, if you want to think about it, of the entire ice shell of Europa and look for these watery environments. So we're pretty excited about Europa Clipper. So what are the challenges here for Europa? Well, I think it's credibly measuring habitability. We need to understand the full context, right? What is the role of those peroxides? What's the role of the subsurface ocean? What are the timescales over which that happens? I think we eventually want to do in situ science. I think everyone who works on Europa wants us to land and do that. We're going to do some sampling, if you want to think about it, with Clipper, with different types of instruments. That's in the late 2020s when most of that science is going to be happening. Hopefully future landers. We've studied some. We really would love one. But we need new instruments. We need new and agnostic biomarkers so that we can actually understand that unseen context I talked about. And I wanted to just mention quickly that this drives analog work here on Earth because we don't know how to answer these questions on Earth. We don't have the instruments, we don't have the technology really to just go into an environment on Earth and say, is it alive? Credibly, without knowing a lot about it beforehand. And so that's motivated our work in Antarctica, and I'm just going to give you a couple of quick highlights because it's fun to do this stuff, and it's motivated by this search for life here as well as on other planets. So what we do is we work in McMurdo. This is near Erebus Glacier Tongue. That's the Mount Erebus. This is what our setup looks like. It's not exactly planetary exploration, but I guess it kind of is. So these are piston bullies and our setup for getting the robot underneath the ice. This is a picture of ice fin going in underneath the water, and part of my team working to deploy it there inside a fish hut at another site that we use. So what we've developed is this robot that's about 12 foot long. It's called IceFin, and it's a modular approach to doing planetary and astrobiology exploration in Antarctica. And so each of these individual sections comes apart, and we can replace science instruments. So really, we think of it as a test bed for a lot of technologies. Right now, we have in situ sensors that can tell us about the organic content, can tell us about the salinity, can tell us about the oxygen content. We're building an onboard microscope, so just funded through the NASA postdoctoral program, we'll be building a flight microscope, if you want to call it, for this vehicle to see if we can actually do that in real time. And so we're exploring under the ice with this vehicle. And what I wanted to talk to you a little bit more was just to end with this unseen context. So these are light-free environments underneath Antarctica's ice shelves, which are essentially unexplored, very, very little exploration, because the ice is so thick, the poles are so challenging to be at. And so what we're able to do with this vehicle that's actually been built both for Antarctica and for future Europa testbed is to get context both from the images but also from onboard sensors as we fly underneath the ice and through the ocean water column in order to understand that unseen context. So I'd just like to leave it there. These are fun to look at, so I could move to my next slide, but I'll go ahead and let these play if folks wanted to ask a few questions. Any questions? None at all. Yeah. Oh.
Quick one. Why are there no plumes in Europa compared to Enceladus?
There are. So there's been recent detections with Hubble Space Telescope. 2 different methods have detected above, kind of 4 to 6 sigma detections of water coming out of Europa. So it's not surprising. In fact, when you look at Europa Clipper's planning, which began, well, it depends on which you want to actually say was the beginning of that, but it was planned to be able to go down to 25-kilometer close flybys of Europa. And the reason for that was that if you scale Europa's gravity and the plumes on Enceladus, that plumes on Europa would probably get to about 25 kilometers and re-impact the surface because it's larger than Enceladus. So the other thing is that the geologic context is different, right? So I mentioned that these water pockets inside the ice shell or some fractures perhaps from the ocean are going to have a different process on Europa. It's a global tectonic system, whereas Enceladus is regional. And so this is a different question. Also important is that we expected those to be there. There was dust detections and exosphere detections and thermal detections during Galileo that told us there were exciting, interesting things there. We didn't have the resolution or the orbits to be able to really confirm that. So we've actually believed since Galileo that there should probably be material coming out of Europa, whether it's from the ocean or from subsurface. Just that's the really question. So it's expected to be there, and we think it's there. Next question.
What are the pressures like on these various lakes and oceans we've been discussing so far? And how do they compare to Earth? Pressures?
So actually at the ice-ocean interface, it's very Earth-like, right? Very Earth-like temperatures, very Earth-like pressures. So Europa's gravity is about 1/10 of that of the Earth, and so you just kind of scale it that way. So the seafloor is maybe a little bit more under pressure, maybe a factor of 2 or so, depending on exactly how deep the ocean is. But it's very Earth-like in that way. Whether the salt characteristics are exactly the same, we don't really know. Estimates go from 12 ppt to 200 ppt, so that would change exactly what the pressure dynamics are at the ice-ocean interface. But it's pretty similar. And so, in fact, the deepest ice on Earth that's actually floating is about 3.5 kilometers on Earth, and that's at Amory Ice Shelf. And so that's actually a very Europa-like pressure that I am hoping one of these days we can take one of these guys to explore exactly that condition. More questions? Yeah.
How does something like this ice fin navigate under the ice? How does the ice fin navigate under the ice? Do you need to use active illumination to see where you're going and what you're collecting?
All right, so the question was, how does it navigate? So in this one, actually a combination of factors. So we have ROV mode and AUV mode. So ROV means that there's a human operator driving it. Obviously, that's not going to work at Europa. So for navigation, we actually use sonars. We use an instrument called a DVL, which is a Doppler velocity logger that basically locks on the ice or the seafloor and tells us how fast we are moving in any given direction. But then it's got also on board what's called an inertial measurement unit, an IMU, and that gives us kind of roll or direction that it's pointed to relative to where we started. And so we use a process right now called dead reckoning, where we can basically track our history as the attitude of our spacecraft / robot is moving under the ice, and then we can kind of track that back using the DVL. So we can pre-program things. One of the things that we're actually working on under this new project is how to teach it to classify ice and drive relative to it. And so that's a thing that a PhD student of mine started working on, and we're hoping to implement on this particular vehicle. But that's the kind of stuff you might imagine eventually doing. We have to take this non-unique process, right, ice crystals and kind of not regular blobs on the bottom of the ice, and teach it to figure out exactly where it is based on that. So working on that as well.
Sure. I have one. You know, beyond the interior liquid ocean, there may be a lot of other perched potential habitats all along fractures, perhaps in Lake Vostok-like melt inclusions, I don't know, at those temperatures. Have you thought about the robotic access to these nearer term or potentially nearer term goals?
Yeah, actually. So one of the important things about this process, I mentioned, so the deepest ice on Earth is about 5 kilometers thick, right? So we've drilled through that. We've drilled down to Vostok. The drilling on Earth is mostly by hot water drills. So essentially it's a super fancy fire hose and a bunch of hot water that you're using to melt through. So that's not really a technology that's going to work on Europa. There's a lot of groups that are actually working on melt technologies. And so whether you want to actually actively drill, hard to imagine a drill bit that can last through 30 kilometers of ice. Maybe 3 kilometers isn't so bad. So if these water pockets are real and are shallow, that would be an option. There's melt probes that are use kind of energy right at the nose of the vehicle to kind of melt water and jet out and kind of steer itself. So there's a number of groups working on that, and then these hybrid technologies. So groups like Honeybee Robotics, there's a group in Europe that's been doing it, Stone Aerospace. So a lot of people are working on the drills. That's why we're working on the vehicle that can maybe go inside of that. So we'd like to turn the drill into a robot that could actually do some navigation. So you could sample as you go along, but in the process of engineering the drills, less science is being done. So we're kind of trying to couple into that. So I think it's a technology that is working on kilometer scales here on Earth. So it's highly probable that this will work as a solution for Europa. And I'm hoping that wherever there's relatively shallow water, there's lots of hypotheses for that, that's where we end up maybe being able to explore with one of these vehicles, any of the vehicles that might be able to land and get under the ice. So like on Mars, we wanted to drive cars around, right? Drive rovers around. The surface of Europa, I would argue, you find someplace interesting and you just go down. And so I think that's really the key.
Okay, great.
Yeah.
Thanks, Brittany.
Thank you.
Thanks.